right, so my name's Ian Sweet. I'm going to be talking about our short paper called Probabilistically Almost-Oblivious Computation. This is joint work with my advisor, Mike Hicks at the University of Maryland and David Darais at Galois. So in prior work, we developed this language called lambda-obliv that ensures that well-typed programs are probabilistically memory trace oblivious. And as part of that project, we implemented as case studies trivial ORAM and showed that it was well-typed and therefore PMTO. And then we followed up with Tree ORAM and recursive Tree ORAM, again, well-typed and therefore PMTO. But unfortunately, when we tried to embed oblivious stacks in our language, we discovered that oblivious stacks are not well-typed. And so this talk is a story about what went wrong, what happened, and how you might be able to fix it. And so the punchline is that we have this slight variant of PMTO, which we call PMTO modulo declassification, that we believe that oblivious stacks will satisfy and will type check in. And so that's what I'm going to describe in this talk. So let's look at an example of trivial ORAM to start. So on this slide, I'm showing you three columns. On the left is the code that's going to be executed on the client. So in this case, we're creating a trivial ORAM of size 6. In the middle is the memory that occurs on the server. And the server can't view this memory. We're assuming that it's in, for example, encrypted RAM. On the right is the memory trace, which is observable to the server. And the server is going to be actively trying to deduce information about our secrets from the memory trace. At the top here, you see a template for the blocks that are going to be stored inside of the ORAM. The position tag field you can ignore for now. That's only relevant when we get to Tree ORAM and isn't used in trivial ORAM. So we allocate 6 cells on the server for our 6 blocks, and we fill them with empty blocks that are ready to be filled by data as the user writes it from the client. So when we perform our first write with a key of 0 and a value of A, the first thing we're going to do is we're going to create a block that represents that data. So the key is 0, the value is A. And for every trivial operation, what we're going to do is we're going to do our linear scan through the data structure. So we're performing a linear scan in the case of write and looking for an empty cell, and we're going to swap one block in and swap the other block out. So we perform that swap. And on the right here, we see in our trace that we performed a read and a write on the first index of the trivial ORAM. Now, in contrast to typical RAM, the trivial ORAM is going to just proceed in a fold-like manner along the data structure. And what we're going to see is that every element of the trivial ORAM is going to be accessed sequentially. If we perform another write, for example, from the key 1 to the value B, we'll see the exact same behavior with every index being accessed. And finally, when we perform a read, it's going to be another linear scan, but we're just going to perform the opposite. We're going to remove the block with the appropriate key, in this case, the key 1. And so what you should observe is that this trace to the right is going to be completely independent of the secrets, because it was the exact same trace no matter which key and value we inserted or removed from the ORAM. So now let's talk about Tree ORAM. So Tree ORAM, as the name suggests, is going to be structured as a tree. So when we create our ORAM, we give a number of nodes for the ORAM, as well as the number of blocks in each node. And in a Tree ORAM, the nodes individually are going to be themselves trivial ORAMs. So when you see an operation on an individual node, it's really a trivial ORAM operation. So we allocate the memory. Again, we fill it with empty blocks. And notice that the position tag field has been ungrayed. We're going to be using that now. So when we perform a write to a Tree ORAM, before we insert the block into the data structure, what we need to do is generate a uniform random position tag, which I'm going to represent as either L or R. And the position tag tells you which direction in the tree to push that block. So in this case, we generate a uniform random position tag, and it turns out to be L. And here's the block that we're going to insert into the data structure. So the first thing we do is we do a trivial add to the root of the data structure. And then the next thing that happens is a process called eviction, in which we pull a random element out of the root of the data structure and push it down to the left or the right, depending on the position tag. And so in order to keep this oblivious, in order to not reveal what the position tag is, we also need to take an empty block and push it down the opposite side in the data structure. So in this case, the right-hand side. And this makes it so that on a write operation, the attacker can't deduce which side the real block was pushed in the tree. So let's perform another write. Again, it's going down the left-hand side of the tree. And again, we see that all of the trace is exactly the same on the right there. And finally, when we perform a read, the position map on the left here is going to tell us, well, if you want to read the key 1, you have to look down the path, the left-hand path in the tree. And that's given by that position tag in the position map. So when we pull it out from the left-hand side, and then remove that value from the position map. And finally, what I want you to notice here is that on the right over here, we actually have revealed, as a result of the read, what the value of our position tag was. But that's fine, because that position tag is never going to be reused, and it was generated completely independently from the secrets. So even though the traces are different, they don't reveal any information about the secrets in the ORAM. So I've been alluding to probabilistic memory trace obliviousness. Let me just drill down on that a little bit. So a program is PMTO if the distribution of adversary visible events, in this case, the memory traces, is independent of any secrets, in this case, the keys and the values that we're inserting into the ORAM. And the language that we previously developed, lambda-obliv, as I mentioned, ensures all well-typed programs are PMTO. But oblivious stacks were not well-typed in lambda-obliv. Now, this could be due to 2 possibilities. So the first one is that oblivious stacks really aren't PMTO, in which case our type system is doing its job by rejecting the program. Or this could be a limitation of our type system, and it's rejecting oblivious stacks, even though they do satisfy probabilistic memory trace obliviousness. And so, as I've already alluded to, the answer is that this is actually a true positive. Oblivious stacks are not probabilistically memory trace oblivious. This was a surprise to us, and the next part of the talk, I'm going to tell you why. So just a little bit of foreshadowing here. Both Trioram and Trioram, as I mentioned, are PMTO. And this is actually despite the fact that the data structure can overflow. So I didn't mention it, but because these data structures have a fixed size, whenever you add something to the data structure, there's a possibility that it's full and that you're going to overflow the data structure and that the block won't properly be added. And so trivial ORAM and recursive Trioram are both PMTO, regardless of the fact that overflow can occur. And actually, in contrast, oblivious stacks are not PMTO, and this is actually caused by the possibility of overflow, as we'll see in just a minute. So let's talk about oblivious stacks. So in this case, notice that we're using a Trioram, first of all, to store our oblivious stack. So that thing you see in the middle is just a Trioram. But I've also added this next field as part of this next component as part of the data field. And this is going to be a pointer to, this is going to be the position tag for the next element in the stack. And so you'll see how that works in just a minute. So we have our empty stack here, 3 nodes, 2 blocks in each node. Now we're just giving the data elements that we want to push. So in this case, we want to push the data element A. So in contrast to maintaining a complete position map, like I showed before, now we're only going to show, we're only going to maintain the key and the position tag for the head of the stack, the most recently added element of the stack. And so in the middle here, you can see the block that we're about to add. Again, it looks very similar to when we were adding things in Trioram, except that this field down here is a garbage value. And the reason for that is because this is the first element that we're pushing into the stack. But in the future, this will point to the next element in the stack. So we push that element down, again, according to its position tag being L. And we update the head key to be 0 and the head position to be L. And now when we push B, it's a very similar process, but notice that here, when we generated our random position tag for this block, it's an R this time, so we're going to push it down to the right. And also notice that this next position tag is an L, indicating that this is going to refer to this block down here. And that was derived from the head position tag that we're maintaining on the client here. So we push that into the data structure. And we update the head key, and we update the position of the head element. But notice that we haven't lost our first element, even though we aren't maintaining it in the position map, because these two things are going to point to this block on the right, and this block on the right is maintaining the position tag for the element before it, for the block before it. It points over there to that block. So when we pop an element from the stack, we'll be able to recover that position tag and then subsequently pop the first element that we pushed. So this is all well and good, but I haven't yet explained why these oblivious stacks actually aren't PMTO. They've seemed just fine so far. So on this slide, I'm showing all of the possible configurations of the oblivious stack after 2 pushes. And the other thing that I've done is I've made the 2 position tags for the first 2 pushes, for the first 2 blocks that I pushed, symbolic here. The first block that I pushed is alpha, and the second block that I pushed has a position tag of beta. And these are all of the 4 possible configurations for those random values and the structure that they induce down here. And so now what I'd like to do is I'd like to show you what happens when we push a third element onto the oblivious stack in each one of these configurations, under the assumption that the block that we're pushing has a position tag of L, meaning it's going to be pushed to the left. Okay, so starting from left to right, we take our fresh block that we want to push and we push it down to the left, no problem there. Second configuration, again, no problem. Third configuration, no problem. And you can see what's going to happen here. We overflow the data structure. Both of the 2 blocks on the left-hand side of the data structure have been occupied already. And so we don't have an empty block to put this third block that we've pushed into the data structure. And so the head key and the head position up at the top left, the head key is going to be incremented to 2, and the head position is going to be gamma, which is left. But as we'll see in just a minute, if we then attempt to pop, things go horribly wrong. So here I've duplicated the head key and the head position for each of these configurations because they're going to differ depending on what happens. So now what I'm going to do is I'm just going to perform a pop on the oblivious stack. So again, from left to right, starting with this block right here, we're going to see that disappear. And the head key and the head position are going to be updated to 1 and to beta, respectively. The reason that this is updated to beta is because, remember, we stored beta, which refers to the previous head of the stack when this block was pushed. So again, for this second configuration, we see that disappear. This is 1, and this is beta. Third configuration, the block disappears, head key becomes 1, head position becomes beta. But for this fourth configuration, what's going to happen? Well, we're going to try to remove it from the ORAM. The head key is going to be updated to 1. And because the block doesn't exist, the ORAM is just going to give us some garbage block back, some fresh, empty block. But what the O stack is going to do is it's going to use the position tag that we got back from the ORAM, and it's going to assume that that thing is the correct position tag, because in all these other configurations, it was the correct value, which is beta. But here it's going to be what I'm representing as a question mark, a uniform random L or R. Okay, so now if we look at the distributions induced by each of these configurations of the head position, notice that in all 3 of these distributions, the head position is completely determined by beta, meaning that in this configuration, the head position is always going to be R, and this one it's always going to be L, and this one is always going to be R. But in this configuration, we get a 50-50 shot at it. And the only other thing that I want you to notice is that these distributions are conditioned on gamma having the outcome of L. And that's because when we popped from the ORAM, that was a tree remove operation. And remember that I said that tree remove leaks the position tag to the attacker through the memory trace. So now if we marginalize over all of these possible outcomes, so each of these is a random uniform value. So each of these possibilities has a 25% chance of occurring. If we then marginalize over all of these things, we'll see that the distribution of the head position, given that gamma was equal to L, over all the possible executions is non-uniform, right? That's pretty easy to see. And the danger here is that if we then perform another pop, what's going to happen is the attacker can observe the non-uniformity of this distribution because, again, the head position is going to be revealed through the memory access trace. So then they can observe that an overflow occurred through the non-uniformity of this distribution. And from an overflow occurring, they can deduce that more than 2 pushes happened in the data structure. And whether or not a push or a pop occurred is considered secret in an oblivious stack. So this is going to leak sensitive information, namely which operations, pushes or pops, were performed on the data structure. So this is the punchline that, this is why O stacks do not satisfy PMTO. But there's a little bit of a question as to why they should have satisfied PMTO to begin with, given that a lot of the papers that originally proposed oblivious RAM and oblivious data structures define oblivious stacks and oblivious data structures as being computationally indistinguishable from uniform. So we expect that oblivious data structures do satisfy this cryptographic definition of obliviousness, but computational indistinguishability allows for a small probability of a leak. So you typically prove computational indistinguishability by proving that the probability of overflow is a negligible function. In other words, it's small. And if you want an example of this sort of proof, lemmas 5 and 6 in the PathORAM paper are a good place to look. But note that from a PL perspective, what this means is in practice, the ORAM size is fixed, and it needs to be close to the working set size of the client, because if not, the probability of overflow can be large enough to actually leak information about the data structure. But only for oblivious stacks, which are only cryptographically oblivious and not PMTO. So the thing to notice is that oblivious stacks are actually almost PMTO, right? If they didn't overflow, they would satisfy PMTO just like Tree ORAM and trivial ORAM. And so our idea is to model overflow in our language lambda obliv as a declassification, which it ought to be because it actually is leaking information. And so we're proposing this PMTO mod or PMTO modulo declassification, which is just PMTO, but with the exception that differences in the trace are allowed to be induced, but only by declassifications. And this is similar to like gradual release, if you're familiar with declassification policies. So here's a summary. We showed that trivial ORAM and Trioram, or verified that trivial and Trioram are MTO and PMTO respectively, despite overflow, but that oblivious stacks are not PMTO, and that this is caused by overflow. And thanks for listening, and I'll take your questions.
Awesome stuff. All right, folks, please chime in, ask your questions. I guess in the meantime, I have some questions. So this is really interesting, and I guess like a really nice example of like if we have principled like languages, they can help us understand things for real. So in your fix, are you imagining? I guess how are you doing the declassification? Are you like, can you do periodic declassification where like maybe you're willing to, admit that you've done, 3 pushes and 3 pops or something like that? Or do you have to do it after? I guess, how do you, yeah, go for it.
So we're imagining that you declassify overflow. So whether or not overflow occurred. And the way that you can do this is you can, so when you construct an oblivious ORAM or an oblivious stack, what you can do is you can have the data structure actually tell you whether or not overflow occurred explicitly in the form of a bit that gets returned by the API. And then what you can do is you can, now that you have a value in your hands, you can explicitly declassify that, just like in, for example, secure multi-party computation, right? Those feature explicit declassifications where you're in the program, you're allowed to say, I'm okay with declassifying this value.
Right.
And so then the idea would be, okay, so you're declassifying overflow, so that's a leak. But how bad of a leak is it? And that's where this cryptographic definition comes in, where you show that it's negligible if you make your ORAM big enough.
Right. I'll read Mike's question too, or answer, not the question. So one idea that we're breaking the problem into two parts: PMTO mod declassification typing, then a separate proof that declassifications are rare. Crypto-style proofs tend to roll these two parts together. Yeah, no, this makes a lot of sense to me. This is really cool. So I'm curious, what are the next things that you're looking at? Like, are you just going through the literature and just like demolishing?
Right. So since this work was done, we've pivoted a little bit to secure multi-party computation. We'd like to kind of merge these two worlds together. And actually this fits very nicely into that framework, because if you want to merge this work with the world of secure multi-party computation, you have to admit declassifications anyway, because secure multi-party computation requires them. And so this is part of what inspired us to take this approach, is because we'd like to be able to do, for example, an oblivious stack embedded in a multi-party computation world. And then what you can do is, you can just repurpose the, explicit declassification of that language. So
Sure.
one big direction is secure multi-party computation and integrating this into a language for doing that. Another possible area to explore is more quantitative, building in the more quantitative notions of obliviousness into the language itself, right? So you could imagine a language that proves through typing or some other mechanism, maybe a static analysis, that the program is cryptographically oblivious, is computationally indistinguishable. Maybe this uses approaches from quantitative information flow or something along those lines, or maybe you steal ideas from Gilles Barthes and uses a lorem logic or something like that. But those are two broad directions that I think are both interesting.
Yeah, that makes a lot of sense. And I guess if you're going to do static analysis, you could potentially even infer to some degree how many pushes you'll really have to kind of like create a stack that's big enough so that you avoid this case, right?
Yeah.
Just to read Mike's comment. So embedding the type system and a logic in the style of semantic typing, then you can use type rules as lemmas and broader proofs of security that involve finer-grained raising, for example, like probability. Yeah, that makes a lot of sense to me.